Right now, as you are listening to this, half of everything keeping modern civilization alive depends on a single element that most people could not name if you put a gun to their head. Not oil, not silicon, not uranium, something older than all of them combined. Something that was forged before our sun even existed, traveled through empty space for billions of years, landed on this planet by pure accident, and was then treated like garbage by nearly every human civilization that ever touched it. And here is the part that genuinely keeps me up at night. Without this one element, roughly 4 billion people alive on Earth today would simply not have enough food to survive. Not in some distant future scenario, not in a war. Right now, today, the food on half the dinner tables on this planet exists because of a metal most people have never once thought about. Cardiac wards in hospitals would go quiet. The air in cities would turn toxic within a generation. And certain cancers that are now survivable would go back to being a death sentence within months of diagnosis. I am not building suspense for the sake of it. I am telling you that we built an entire civilization on top of something we do not see, do not discuss, and for most of history actively threw away. This is the story of iridium. Element number 77, a metal born in the most violent event the universe is capable of producing. Delivered to Earth like an unwanted package, ignored for centuries, and then quietly woven into the foundation of everything we depend on. And the reason I want to tell you this story is not because of the science, though the science is extraordinary. It is because of what this metal reveals about us, about how we look at things without seeing them. About how many times in history the most important discovery was sitting right in someone's hand, while they complained about it being in the way. We are going to go all the way back, before the Earth, before the Sun, before anything in this solar system existed at all. Because that is where this story actually begins, and if you skip that part, nothing else makes sense. But before we get there, I want you to hold one image in your mind. Somewhere right now, in a research hospital, a patient is receiving an intravenous treatment that contains atoms of this element. Those specific atoms were forged in a cosmic collision that happened before our planet existed. They traveled here inside a rock from space. They were mined from a thin geological seam deep underground. They were purified, processed, and dissolved into a compound that is now flowing through a tube into a human vein, locating cancer cells and destroying them from the inside. From a dead star to a hospital drip, that is the journey we are about to trace together, and I promise you, every single step of it is stranger than anything I could invent. Friends, if this kind of story is something you want more of, subscribe and leave a like. It genuinely helps more than you might think. So, let us talk about how iridium is actually made. And I mean made in the most literal, physical sense, because it does not come from a star burning normally. A regular star, even a massive one, produces elements up to iron and then stops. Iron is where the math changes. Beyond iron, fusing atoms together costs more energy than it releases. So a normal star simply cannot do it. Iridium has 77 protons in its nucleus. A normal star cannot get anywhere close to building that. What you need instead is something that sounds less like astrophysics and more like the end of the world. Two neutron stars colliding. A neutron star is what remains after a massive star explodes at the end of its life. The core does not explode. It collapses so completely that electrons are forced into protons and the entire object becomes a sphere of pure neutrons roughly 20 kilometers across. Take a mountain range and compress it into something the size of a mid-sized city. That is approximately the density we are talking about. One small spoonful of neutron star material would weigh more than every building, every bridge, every car, and every human being on Earth combined. Now imagine two of those objects orbiting each other for longer than the Earth has existed, slowly spiraling inward as they bleed energy away into the fabric of space-time itself. getting closer by a fraction of a millimeter per orbit, for billions of years. And then, finally, contact. The collision releases more energy in a fraction of a second than our Sun will produce across its entire 10 billion-year lifetime. The temperature at the point of impact reaches levels that make the core of the Sun look mild. And in that extreme environment, atomic nuclei begin absorbing neutrons faster than physics can stop them. Heavy elements are assembled almost instantly: gold, platinum, iridium. The debris of that collision is flung outward across light years of space, a cloud of newly forged atoms expanding through the galaxy. Eventually, some of that cloud drifts into a region where gas and dust are slowly condensing under gravity. A new star begins to form. Planets coalesce around it. One of those planets is ours, and buried inside the rock and dust that builds the early Earth are atoms of iridium that were made in that ancient collision, long before our Sun lit up for the first time. The metal was here from the very beginning, waiting. And what the young Earth did with it next is almost cruel in its completeness. Every single atom of iridium that was present when the Earth first formed is sitting right now at the bottom of a pit 3,000 kilometers beneath your feet, completely unreachable, locked inside the planet's iron core for the rest of Earth's existence. Let that sink in. The iridium that arrived with the original protoplanetary material, all of it, every last atom, sank. The young Earth was entirely molten, a churning ocean of liquid rock with no surface, no crust, no floor you could stand on, just heat and pressure and gravity doing what gravity always does. Heavy things go down. Iridium is one of the densest elements in existence. Its density is so extreme that a block of it the size of a basketball would weigh more than most people do. So when the young Earth was molten and everything was slowly sorting itself by weight, iridium did not linger near the surface. It dropped. Straight down. Through thousands of kilometers of liquid rock, settling toward the center along with iron and nickel, disappearing into a depth that no drilling technology we have ever built or imagined could reach. By the time the Earth's surface cooled enough to form a solid crust, the iridium content of that crust was essentially zero. Not rare, not scarce, essentially absent. If the story had ended there, iridium would be the most irrelevant element in the periodic table. A metal that exists on Earth in theory, but is reachable by no one, useful to no one, known to no one. The entire arc of this story, the hospitals, the catalysts, the food supply, none of it would exist. But the story did not end there, because the solar system was not finished with us yet. For a period lasting tens of millions of years, long after the Earth's crust had solidified, the inner solar system was being continuously pelted by rocky bodies from further out. Asteroids, fragments, debris left over from the formation of the planets, falling inward and impacting the young Earth in a relentless, slow bombardment. And those rocks carried iridium. Not because they were special, but because they never went through the same differentiation process the Earth did. They were never molten all the way through. They never sorted themselves by density. Their iridium stayed distributed through their bulk, and when they hit the Earth and broke apart and were absorbed into the crust, that iridium stayed near the surface too. It did not have time to sink. The crust had already solidified. The window for sinking had closed. So the iridium from those incoming rocks was effectively frozen into the upper geology of the planet, mixed into rock formations near enough to the surface that billions of years later, a human being with the right equipment could actually reach it. Every gram of iridium that has ever been mined in human history came from that second delivery, from rocks that fell out of the sky after the planet had already formed. We are not mining the Earth. We are mining the remnants of an ancient bombardment. And the places where those remnants concentrated most densely are specific, limited, and very far from most of the world's population. So picture this: a merchant in a busy trading post somewhere along the old routes connecting the eastern and western edges of the ancient world. The air smells like dust and animal hair, and the sharp tang of whatever the person next to him is cooking over a small fire. He is examining a handful of small, dense nuggets that a traveler just offered him. Gray, almost silver in color, heavier than they look. The traveler says they came from riverbeds near mountains to the Far East, that local people there sometimes collect them, that they do not rust or tarnish no matter what you do to them. The merchant picks one up and rolls it between his fingers. It is cold in a way that feels almost wrong, like it is pulling heat out of his hand rather than warming up from it. He presses it with his thumbnail. Nothing, not a mark. He drops it into a small cup of the acidic solution he uses to test silver. Nothing happens. No fizzing, no discoloration, no reaction at all. He fishes it back out and looks at it. Still the same. Still that flat gray shine. He sets the nuggets down on the table and pushes them back toward the traveler. Not silver, not gold. Reacts with nothing. Marks with nothing. He cannot sell something he cannot identify to a buyer who will test it the same way he just did. The traveler shrugs and wraps the nuggets back up. Down the road, another merchant does the same test. Same result, same conclusion. The nuggets travel from hand to hand across hundreds of kilometers of trade routes, passed off for almost nothing, occasionally used as counterweights on small scales, because at least their density makes them useful for that. An element that will one day help feed half the planet, sitting on a market table being used as a paperweight, while the men around it argue about the price of copper. The greatest minds in European chemistry spent over a century trying to melt iridium, and every single one of them failed completely. Not partially, not almost, failed. Walked away from their furnaces with nothing but a slightly warm gray lump and a notebook full of confused observations. And these were not amateurs. These were the people who figured out how combustion works, how acids behave, how metals bond and dissolve and transform. They could smelt iron, refine silver, separate copper from its ore with their eyes closed. But iridium sat in their crucibles, like a stone sitting in a river, absorbing everything they threw at it and giving nothing back. The reason is simple but brutal. Iridium melts at 2,446 degrees. Write that number down somewhere in your mind and hold it. 2,446 degrees. The best furnace a European workshop could produce in that era, running at full capacity with a full team working the bellows, reached somewhere around 1,300 degrees on a very good day. That gap, more than 1,000 degrees of missing heat, was not a technical inconvenience. It was a wall. A physical wall built by the laws of chemistry that no amount of skill or effort or cleverness could overcome with the tools available at the time. Researchers documented their failures in meticulous detail. One account describes heating a small sample for 6 continuous hours, the furnace glowing so hot that the assistants had to wet cloth and hold it over their faces to keep working. At the end of 6 hours, the sample had changed color slightly on the surface. That was all. Another researcher tried combining iridium with other metals to lower the temperature at which the mixture would flow. The same trick that works with many stubborn materials. Some combinations softened slightly. None produced anything close to a workable result. The metal just sat there, radiating a faint orange glow when pushed to the limit of what any furnace could do, and then cooling back to its original form the moment the heat dropped. Unchanged, unmarked, indifferent. And here is what makes this period genuinely strange to think about. While these researchers were failing, iridium was already understood to be extraordinarily valuable. Not in the way gold is valuable because people agree it is. Valuable in the way water in a desert is valuable, because it does something nothing else can do. Its resistance to heat, its refusal to react with almost any chemical, its density, all of these properties made it theoretically perfect for precision instruments, for laboratory equipment, for applications where even the smallest contamination or degradation would ruin everything. Everyone could see what it was worth. No one could touch it. It took a completely different approach to finally crack the problem. Not more heat, but chemistry. A researcher in Central Europe, working with a small team in a private laboratory, found that iridium could be coaxed into dissolving under very specific conditions involving a mixture of concentrated acids at elevated temperature and sustained exposure over many hours. Once dissolved, it could be precipitated back out as a compound, and that compound could be processed at temperatures that were actually achievable. The resulting material was not perfect, but it was workable. For the first time in history, human hands could shape iridium into a usable form. And the moment that became possible, everything that followed began to accelerate. What happened next is one of the most quietly dramatic decisions in the history of science, and almost nobody talks about it. A chemist named Aldrich Fennin, working in a well-funded private laboratory in the north of England, independently developed a cleaner and more reliable version of the dissolution process. His method produced iridium of a purity that nobody had achieved before. Consistent, repeatable, scalable. He ran the process himself dozens of times, documented every step, and then sat alone in his laboratory one evening, looking at a small polished piece of the finished metal sitting on his workbench. The light from his oil lamp caught it and threw a cold silver gleam across the ceiling. And Fennin did not write up his findings for a journal. He did not send letters to colleagues. He sat with the knowledge for 3 days, and then he made a decision that would shape the next several decades of his life. He buried the method. Here is why. Iridium's density sits just above gold, a fraction higher in fact, which means that if you took a bar of iridium, shaped it to slightly smaller dimensions than a standard gold bar, and coated it in a layer of gold thick enough to survive casual inspection, the bar would register the correct weight on a scale. It would pass a surface scratch test. It would look, feel, and weigh exactly like what it was pretending to be. In an era when international trade ran entirely on the trusted weight of metallic currency, when banks and governments and merchant houses all operated on the assumption that a bar of gold was simply a bar of gold, this was not a minor vulnerability. It was a crack in the foundation of the entire financial system. Fennin understood that publishing his method meant handing that crack to anyone who could read. So instead, he began producing iridium products quietly. Crucibles for high-temperature laboratory work, precision weights for scientific instruments, small components for specialized equipment. He sold them through a network of intermediaries who did not advertise the source. For years, nobody outside his immediate circle knew where the best iridium components in Europe were coming from. He grew wealthy, and the method stayed locked in his private notes. The irony that a metal resistant to every chemical reaction was being kept secret to protect the world from a financial reaction was apparently not lost on him. His private correspondence from that period contains exactly one line referencing the situation, written in the margin of an otherwise routine inventory note. It reads simply, "Some knowledge protects best when it sits still." Fennin's secret eventually leaked, as all secrets do. And the first thing that happened was exactly what he feared. Within a few years of his method becoming known to a small circle of chemists and metallurgists, reports began surfacing from banking houses in 2 different countries of gold bars that were not gold bars. Not crude fakes, not the kind of thing a street trader might try. These were sophisticated, carefully constructed bars that had passed through multiple rounds of professional inspection before someone, by accident, noticed that the dimensions were slightly off for the stated weight. When the coating was removed, what was underneath was a dense gray metal that matched no material the inspectors had previously encountered. The financial damage from those specific incidents was significant. The reputational damage to the institutions involved was worse. And Fennin, reading about it from a distance in his later years, apparently said nothing publicly. He had predicted it exactly. He had tried to prevent it exactly. And it had happened anyway, precisely on the timeline he would have expected, given when his method began to circulate. But here's the thing about iridium that makes this entire chapter of its history almost funny in a dark way. The fraud was possible only because of the very same property that made iridium so scientifically valuable: its density, its refusal to be anything other than exactly what it is. The quality that made it perfect for precision work was the same quality that made it perfect for deception. One element, two completely opposite uses, driven by the exact same physical characteristic. And while bankers were quietly panicking about their gold reserves, a completely different group of people was looking at iridium and seeing something else entirely. They were not looking at it as a commodity or a threat. They were looking at it as the only possible answer to a problem that had been quietly destabilizing science and commerce for decades. The problem of measurement itself. Of how you define, with absolute precision, what a kilogram actually is. And their solution, when they finally arrived at it, would put iridium at the center of something no metal had ever been trusted with before: the literal definition of physical reality. Here is a problem that sounds philosophical until you realize it has actual practical consequences. If every country measures weight differently, and if those differences are small but real, then every transaction, every trade deal, every scientific experiment that crosses a border is built on a foundation that is slightly, invisibly wrong. In the era when this problem became impossible to ignore, international trade was expanding rapidly, scientific collaboration between countries was becoming standard, and the idea of a single universal system of measurement was moving from idealistic proposal to urgent necessity. A group of scientists from multiple countries convened to solve it. They needed a physical object that would embody the definition of 1 kilogram, not represent it, not approximate it, be it. The object would need to be the same in 100 years as it was on the day it was made. It could not rust. It could not react with the air around it. It could not absorb moisture or shed atoms or change in any measurable way across generations of storage. They went through the available options methodically. Every common metal failed on at least one criterion. Gold was too soft and reacted with certain compounds over long timescales. Steel corroded. Silver tarnished. And then someone brought iridium into the conversation. Not pure iridium, because pure iridium, despite its extraordinary properties, is brittle enough to chip under certain conditions, but an alloy of iridium and platinum, roughly 9 parts platinum to 1 part iridium, that combined the chemical inertness of both metals with a hardness that pure platinum alone could not provide. A small cylinder was machined from this alloy, with a level of precision that was essentially the limit of what the technology of the time could achieve. The surface was polished until it reflected like still water. The height and diameter were made equal, a proportion that minimizes the surface area relative to volume, which minimizes the amount of the object exposed to any possible contamination from the air. That cylinder was placed in a controlled environment and declared to be, officially and legally, 1 kilogram. Not a representation of a kilogram, the kilogram. Every scale in every laboratory in every country that signed the agreement was calibrated against copies of that cylinder. Every copy was calibrated against the original. The original never moved unless absolutely necessary, and when it did move, it was handled with tools, never with bare hands, because a single fingerprint contains enough material to alter the mass of the object at a level that the most sensitive instruments could detect. For well over a century, that cylinder sat in its vault. Wars happened around it. Governments collapsed and reformed. The borders of countries shifted. The cylinder did not change. And then, eventually, scientists began comparing the original against its copies and found something deeply uncomfortable. The numbers did not quite match. And nobody could say with certainty which one had drifted, because by definition, the original was always correct. There is a metal sitting inside your body right now that your immune system has never once tried to attack. And the reason it is there traces directly back to a contaminated laboratory experiment that a researcher almost threw away as a failed result. But before we get to that, let me finish the thread we left hanging. The cylinder in the vault. The kilogram that was also its own definition. The comparison checks that showed the copies and the original were drifting apart by amounts too small to see, but too large to ignore. The scientific community stared at this problem for decades. The logical trap was airtight. If the original is the definition, then whatever it weighs at any given moment is, by definition, correct. There is no external reference to check it against. You cannot stand outside the system and measure it from a neutral position. The system is the system. And yet everyone involved knew something was wrong, because the copies were not agreeing with each other either, which meant the divergence was real, even if you could not pin down where it originated. The solution that finally arrived was radical in the cleanest possible way. Stop using a physical object entirely. Redefine the kilogram, not in terms of a thing you can hold, but in terms of a constant of nature that does not change, cannot change, exists identically everywhere in the universe, regardless of temperature or air pressure, or how carefully someone handled it last Tuesday. A fundamental physical constant was fixed to an extraordinary number of decimal places, and the kilogram was mathematically derived from it. From that point forward, the cylinder in the vault was no longer the kilogram. It was just a very precise, very old, very well-preserved piece of metal that had done an extraordinary job for over a century and was now retired. Scientists went to retrieve it for the formal handover comparison. Opened the vault, removed it carefully with the same tools that had always been used, and measured it one final time. It had not changed. After everything, after all the wars and the political upheavals and the shifting of entire scientific frameworks, the iridium alloy cylinder was exactly what it had always been, which, if you have been paying attention to this story, should not surprise you at all. But what happened next, in a completely different field, in a completely different country, is the part that still genuinely moves me when I think about it carefully. A researcher named Callum Vesh was working in a university laboratory studying how biological membranes respond to sustained electrical stimulation. His subject was simple bacterial cultures, easy to grow, easy to observe, well understood. The goal was straightforward. Apply controlled electrical current, observe changes in cell behavior, document the results. To do this, he needed electrodes, and he chose an iridium alloy for the same reason everyone in the story so far had chosen iridium for precision work. It does not react. It sits in the system without interfering with it. It is, by every standard definition, chemically neutral under normal conditions. He set up the experiment, ran the current, and the bacteria stopped dividing. Not slowing down, not dividing less frequently, stopped. Vesh assumed contamination and reset the experiment with fresh cultures. Same result. He checked the current parameters, checked the growth medium composition, checked the temperature, checked everything on his standard protocol list. Everything was within normal range. The bacteria still were not dividing. It took him several weeks of systematic elimination before he arrived at the electrodes. And what he found when he analyzed the growth medium carefully was that the iridium alloy, under the specific electrochemical conditions of his experiment, in the presence of certain compounds in the medium, was releasing trace amounts of a complex molecule into the solution. That molecule was interfering with the cellular machinery responsible for replication. It was not killing the bacteria. It was specifically, selectively, blocking their ability to copy themselves. Vesh was a careful enough scientist to recognize that this was not an obstacle to his original experiment. It was a completely different experiment, and possibly a much more important one. He shifted his entire focus. Animal studies followed, then carefully monitored human trials in collaboration with a medical research team. The compound worked on rapidly dividing cells. It disrupted their replication cycle with a precision that no existing treatment could match for certain tumor types. The survival rates for patients with specific cancers that had previously been extremely difficult to treat began shifting in a direction that oncologists had not seen before. Not gradually, sharply. The kind of shift that makes researchers check their data 3 times before they believe it. And now think about what you are actually looking at when you hold all of this together. A metal forged in the collision of 2 dead stars, delivered to Earth inside rocks that fell from the sky after the planet had already formed, passed from hand to hand across ancient trade routes and dismissed as worthless ballast, defeated every attempt to work with it for over a century, kept secret by the one man who cracked it because he understood it was too powerful to release carelessly, used to define the most fundamental unit of mass in human civilization, and then found, by accident, inside a contaminated laboratory experiment to be capable of stopping certain cancers in their tracks. One element, 77 protons, a melting point that beat every furnace that ever tried to conquer it. And now sitting in hospital drip lines, in precision instruments, in the exhaust systems of vehicles, in the hearts of patients with pacemakers whose bodies have never once recognized it as foreign. We built more of our world around this metal than most people will ever realize, and we did it without ever fully planning to. Every major application of iridium in human history arrived sideways. Through accident, through failure, through someone being stubborn enough to keep asking why something was not behaving the way it was supposed to. The metal did not change to accommodate us. We changed everything around it to accommodate the metal. That is the moral of this story, and I think it applies far beyond chemistry. The most important things do not announce themselves. They sit quietly in the way, heavy and unreactive and inconvenient, until someone finally stops complaining about them being in the way and starts asking what they actually are. So here is the question I want you to sit with. What is sitting in your life right now? Something you are treating as an obstacle, something you are working around and dismissing as noise that might actually be the most valuable thing in the room. Write your answer in the comments. I want to know what you think. And if this story made you see something differently, leave a like and subscribe. There is much more where this came from.